you could instead. So say this is where it's positive and this is where it's positive. So that the derivative function must be above at that point. So you know it's going to come down to there, but you know it's going to go up and then down here. How do you know it's going to go up and then down? Because it has to be glued to those points. So everywhere else the derivative has to be what? So it has to be below the x-axis. So you know it's going to go down and then up, and then this part is just going to go down.
I have a question.
Yes, go ahead.
Isn't it getting...
What are some interesting points on the derivative? What are some interesting points on the derivative?
The x-intercept.
The x-intercepts of the derivative are interesting because you use those to nail them down. But what points have we not found actually, or what points have we not labeled that would be interesting to find?
Y.
Oh, we're across. That could be one. That could be one. Where else?
The peaks.
The peaks. So one thing we could talk about here is the peaks of the derivative. So the peaks of the derivative happen right here and right there. What do those points correlate to on the original function? The derivative is going to be really negative or really positive, or the highest positive and the lowest negative when what is true about the original graph? When it's what? The derivative represents the rate of change. So if the derivative is high, what does that mean about the rate of change? It's high. It's high. So if the derivative is really, really low, it means the derivative is going to be really steep, and it's going to be steep, right? So if you're at the lowest derivative point, what does that mean? What does it have to correlate to? What's happening here? Steepest, right? And what's happening right there? What's happening right there? Steepest. So wherever you make the highest and lowest points of the derivative, it has to correlate to the steepest parts of the function. Does that make sense, everybody? And you kind of did it over there naturally. You see how you did that right there? It's not always going to be halfway because these curves aren't always going to be symmetric, but the idea is you don't know how high it's going to be, but you know it's going to be highest above the steepest point, because from the steepest point it has to be the largest derivative. Good job on that. Okay, is this seen this notation before? What do you think of this notation? What do you think that means?
The short.
Just what do you think that notation means? What is it saying use? Change in x. So what's another way of saying that? That is y prime. That's the derivative. There are many ways to say the same thing in calculus. It's a good question why. In my calculus, I'll try to pull it out of the BC calculus book. There's probably 6 common ways to state derivative. I think it's because you use derivative in so many fields of math that it's been folded into the notation of those fields. Okay, so given that function, find the equation of the tangent line. Find the equation of the tangent line. Go ahead. No hints. Try to find the equation of the tangent. How many things do you need to write the equation of a tangent line?
3.
Well, yeah, it depends on how you break it up, right? You need a point and a slope. How did you get the point? Yeah, you do f of 2, and then what do you find out? I think it's 4, or what is it? 22? Way off! Okay, and then how do you find the slope? You find the y prime, the derivative. So you do y prime. So you could, another way to write that would be f prime evaluated at 2. And I think it's 30, is it 31? 41. Is it 41? So then you glue this all together. Y minus 22 is equal to 2 times?
No, 41 times.
Oh, man, I'm just off my game today. I'm glad you guys are paying attention. X minus 2. Do you guys agree with that? So when you're working with polynomials, is your life kind of nice? Your life is kind of nice. Now, so Alex, I see you did it to slope-intercept form. Unless I force you to do that, you can leave it just like this in point-slope form if you want to. It's totally fine. It's totally fine. Okay, so let us... What's different, Arvin?
Harder to simplify.
Well, what do you mean? What's harder to simplify?
Well, like you can't just do 2x. Or
You can't just do what?
2 over 3x to the negative first.
Okay, I understand what you're saying. So you can't do that. Why are you motivated to do that in the first place?
Because then you could turn it into a power function.
Turn it into a power function. So the thing is, what can't you use on this?
The shortcut.
There's no shortcut. You don't know a shortcut for this one. You don't know a shortcut, right? So what would you have to use on this one? What's it called? The limit definition of derivative, right? And what is that limit definition? Can someone tell me the limit as what goes to 0? H goes to 0 of f of a plus h minus all over h. So if we're finding the derivative, if we're doing it at x equals 2, what are we plugging in for a? 2. So we'd be doing the limit as h goes to 0 of f of 2 plus h minus f of 2 all over h. Okay, that's nice. Now, does the algebra get a little annoying? Sure. What would this look like? Do this for me right now. Go up to the board. Go up to the board and figure out what the limit will be. Don't evaluate the limit, but write down what the limit will be once you apply this function to this. Tell me what it's going to be and put a box around it. 8 over 14 is right there. And then what's that whole thing over? It's all over h. So let's see what happens when we try to simplify this. Now, when you're simplifying this, do not try to simplify everything all at once. Simplify a numerator, simplify a denominator. So if I were to do that, what does the numerator here become? Can someone just tell me what that becomes? 4 plus 2h, yep. Plus 4. And who wants to tell me what the denominator is right here? What's that one going to be? Well, 3 times, and then 2 plus h squared plus 2 minus 4/7 all over h. Now, why can't you just plug in 0 for h right now? You still have h in the denominator, so if you plugged in 0 for h, what happens?
It's undefined.
It's undefined, exactly, so you can't do it. So what are you hoping you do? If you continue this algebra, everybody, if you continue this algebra, what are you hoping happens? It cancels, you hope you cancel the h. Okay, get back to the board with somebody you're not sitting next to right now, next to one of your starts, and try to finish the algebra on this. Try to finish the algebra on this. Place, and you were like, frowny face. Why did you think frowny face at this point?
It looks like a wall.
Yeah, but what's the specific thing? What's the specific structural element that makes it so you're not a super fan of it?
It was a cross-eyed. Like now it's like
There's nothing easily to cross out, right? But the thing is, what's that numerator? It has 2 fractions. To subtract fractions, you need a what? You need a common denominator. So if you're going to create a common denominator, which you do different ways, you can either multiply by this one, you multiply by, oh look, this over that, and then this one, you just have 7 over 7, and now h is along for the ride. You have a common denominator immediately, and then you hope that things cancel out enough so that you can eventually cancel the what? You want that h to go away, right? So when you do this, there was a magical thing that happens. You see the highlighted blue right there? What ends up canceling out? Why is it really key for that 56 to cancel out? Because there's all h's in the rest. So therefore, there's something for it to cancel with. If that 56 stuck around, are you kind of stuck? So hey, that 56 cancels. Oh, and then the h, oh, look at that. Those 8, oh, look at this. H goes to 0. It simplifies to negative 17 over 49. Here's the thing. Just as a precursor to the, as a preview of what's to come, we had a quick way of doing polynomials. Is there going to be a quicker way of doing rational functions? Yes. Is it going to be as nice? Is it going to be as straightforward as the power rule differentiation? No, but it'll help you. It will help you. It will help you. Yes, this one was, and if I gave you number 1 with only the information that you have at hand, do you have a quick and perfect way of differentiating y equals 2 to the x? Do you have a rule yet? No, you would have to use the what? What's it called? Limit definition of derivative. Limit definition of derivative. You'd have to use the
Limit definition.
There it is, right. And that's not quite perfect for you because you have to decide how many decimal places to go to. There is something on your calculator that helps you find derivatives. So everybody, stand up, do not to the x as our function. Now your calculator might express this a little differently. The typing might work a little differently. You might have a caret sign instead. So we're gonna have to work through that, but it's functionally the same. So that function is now y1. That function is now y1. Now if you go to math, go down on the first column here, you'll see a lot of different functions. Fmax, Fmin. Which one do you think it is? Oh, there it is. nDeriv, right there. I'm going to press enter here. And look what it gives us here. You see this here? This is written slightly differently than some of your calculators. I think most of them will say this is math print. It's like the upgraded version. It's more natural math writing. So it's asking you what you're taking the derivative with respect to. We're in single variable calculus. What's the only variable we work with when we're doing derivatives on the calculator? X. So you literally put the x right there. And then this is what function are we taking the derivative of? What function are we taking the derivative of? 2 to the x, but we entered it in as y1. It's really important because the more times you have to type a function, the more chances you have to do what? Mess up. So if I go vars, y vars, function y1, y1 is there, and I can just call y1. And what do you think that bar with the x means? What, do you want to take a guess? Not divide, it means evaluate at. So this means take the derivative with respect to x of the function y1 at, and what did it ask us for? I think 2?
1.
Oh, is it 1? Okay, it's 1. So we type 1 there and we press enter, and look what it gives us. It just pops out the derivative. So can you actually do that for any function? It's effectively literally, the calculator is effectively using the limit definition, and it's making closer and closer estimates. Kind of. But this is just an estimate. Did it do calculus? No. It has an algorithm that it follows, because what are calculators really good at doing? Calculate. No, they're really good. They're really good at calculating, but algorithms, repeated, like to a calculator, division or multiplication is almost instantaneous, right? So if you say do 1 billion divisions, like, okay, done, you know? But algebraic manipulation, that's a totally different thing. That's programming. So we go back into here, and we can say, okay, if we now know, let's just do this. I think it's going to put it over to the side. Yeah, no, it did it. Hey, that's cool. Okay, so we just found the slope. How many things do you need to find for the to find the equation of a line? We have the slope, so now we just need the what? What is the? Can someone just tell me what the point is? 2, 2. 2, 2, because 2 to the first is. Oh, 1. Oh, so it's 1 comma 2 to the first, so it's 1, 2. So can someone just tell me what the equation is to 3 decimal places? Can someone just read me the equation? What's it going to be, Arvin?
Y minus 2.
Yep.
Times 1.38.
6. Yeah, sure.
Or 6.3.
That's fine. Times.
X minus 1.
Done. Excellent. Fantastic. Fantastic. You're done.
6.3.
It's okay. It's totally fine. There's actually 2 ways to round.
Yeah.
On the AP test, they actually they give you they let you do 2 things, either truncate or round. Truncate means just chop everything off after 3, or if it's like a 9, round up. 5 up from 5. They accept either one because it's either way is considered rounding. Now on number 2, you would have to use the same method, because do you have any idea how to find the derivative of cosine algebraically? No, not algebraically. So instead, what could we do? We could literally go into our calculator, and instead of y1, what do we write for here instead? Cosine of x, right? There's a really cool thing on your calculator. Do you know entry? Above the enter button. Above the enter button right here in blue, there's entry. Do you know what that does? If you do second enter, look what happens. The last entry comes up. Oh, I pressed enter by mistake, sorry. What can I then do? Instead of 1, what do I put in? Pi divided by what? 3? Oh, not 33. What'd you say?
It's Y1.
Because I changed y1. I changed y1, so it's calling a different function. So when I press enter on this, what is it doing? It's doing the derivative of y1 with respect to x, because it's dx, of the function cosine now, and it's evaluating it at what? X equals pi over 3. It's doing the derivative of cosine at x equals pi over 3. And we press enter. Oh, look. There's the answer. So what's really, really powerful about this is, really, honestly, your calculator can do a lot of things for you, but the 2 things that are going to be most helpful for you are going to be calculating derivatives and calculating later. What are we going to calculate? Does anybody know? Anybody know what the opposite of differentiation is effectively? Anybody? It's called integration. Oh, wait, so we used our calculator. So what's the equation of the tangent line going to be, Lindsay? Y minus? Anybody know? Y minus what? Come on, y minus? What's cosine of pi over 3? What's cosine of pi over 3? What is it? No, cosine of pi over 4 is 2 over root 2. What's cosine of pi over 3? Adjacent. It's 1/2.
Yeah, I need 1/2.
0. Oh wait, negative 0. What? 8. Oh, I can almost write it. Negative 0.866 times what? X minus. What happens if I did this derivative and it came up with like a really, really, really weird answer? What would I need to check? Mode. What mode do I want you in?
Radian.
What mode? I want you in radians. Now here's the thing. The work I just showed you, what I just showed you with your calculator, does the calculator care what type of function it is?
No.
Does it care how complicated it is? No. So you see that function right here? This looks super complicated. It's more complicated, right? But what can you use to do these things? You can use your calculator. Yes, Alex.
Would you ever want to do a problem like this in degrees?
That's a really